So I'm Kieran, part of the marketing team here at Geeq, and we are very blessed to have with us here today founder John Conley.
Hi, Kieran. How are you?
Very well, thanks. Hopefully you are as well.
Good.
Tech's not my strong point, apparently, so we'll go through this as well as we can. The project's obviously unusual on the basis that we've pretty much joined you, and you've been going from the ground up for what feels like a very long space of time with all of your credentials. I mean, do you want to intro a little bit as to what we've got today lined up for people?
Well, let's see. So I guess the main point is just to sort of give everybody an update of where we are in the development, the code writing, and so forth, and perhaps give a little bit of background of how we got here, and so a little glimpse of the future where we hope we're going.
Sounds fantastic. I mean, some of the common threads, of course, that we kind of touched base on between ourselves with Stephanie, yourself, Hans, and obviously all the rest of the core team of developers as well, were things that we might look at covering, things such as data and communication security, which I know you're very enthusiastic about, and making sure it's done the right way.
Yeah, we have a different philosophy, I suppose. I always believe that if you can be hacked, you should be hacked because you will be hacked. So I assume the enemy is already in the gate, and trying to build a strong enough gate to keep them out is just an exercise in time. Eventually, the enemy is going to get through. But if you design a system so if the enemy is already through, there's nothing he can do, well, that's a much better guarantee. And so that's how our edge security works. The enemy can do whatever they like, but you're still in control. You're able to see what the state of your account is and to prove that it's correct and nobody has tampered with it. And if somebody tries to pay you out of an account that has been tampered with, it's also visible to you. So it really doesn't matter if we have malicious consensus that comes and says red is blue, because red is not blue, and you don't have to change your mind.
Yeah. Powers in yourself. You can almost check it yourself and make sure it's correct, can't you? Verify.
Yeah. So if you can't trust yourself, then we can't help you. But if you can trust yourself, then we're good to go.
And this year, 2020, it's been a big year to learn how to do that.
but having said that, so we are concerned about security otherwise, because people can imitate other people. So we've got our cryptographic security protocols that are based in a key called an Edwards 448 key, which has some advantages. It's relatively computationally efficient, but it also gives significantly more bits of security than we'll find in the keys that Ethereum are using. So Ethereum has keys that give you 128 bits of security. We've got 224, which pushes off the threat of quantum for quite a few years. I mean, ultimately, quantum will be able to break this, but by that time, we'll have a way of migrating to something better. But we'll be the last to go down. The lights will go off for us. So that's a compromise, because it does take some more computation. It does take some more bandwidth, which is one of the things we try to minimize.
Oh, cool. So in essence, you're looking at your low data costs and upkeep as well, to make sure that you're not just too secure but costing so much.
Right, that's right. I mean, you can build yourself a titanium bolt that's 5 meters thick, but that's too costly to be practical, and that's not what we want to do.
No, yes, exactly. You need to weigh out the cost, and then of course, with it not being costly or too costly, this thing ties in with the whole IoT and the way that Rick and yourself come together to bring all of the information together. Yeah.
Excellent point. Well, that's right. If you can't do this on a simple device, then it loses a lot of its utility. There are, for example, Hashgraph, for example, there are studies that show that actually IoT devices mostly don't have the bandwidth, and actually don't have the power, the literal power in terms of electricity to be part of the network. Most IoT devices run at 1% of their power rating because they're in sleep mode. And if they're constantly having to communicate with the network to say, you're still doing things, well, then their battery's gone almost immediately.
Yeah. No, wow.
Yeah, that's part of our design.
I love it. I'm looking forward to seeing when these little tiny features are able for us to try ourselves without even showing.
Yeah, me too. Me too. It's always too long. Yeah, so we focused on both data, minimizing the data requirements and minimizing the communications requirements. Part of that is our use of something called Captain Proto, which is a sort of improved version of Protobuf by the guy that actually wrote Protobuf. And it's a way of encoding data that's very precise, very rigorous. It deserializes in a deterministic way, and it's efficient. It's designed to use what's called RPC, which is remote procedure call, instead of HTTP. So
Okay.
it's a way that machines are really supposed to communicate with one another using APIs, and as a result, it doesn't have the generalness and the overhead and sort of the wasted bandwidth. It's not wasted for HTTP because it's got a different intention, but these are like packed little data packets that are much better suited for the purposes that we're using them. So all of these decisions are meant to just shove down the cost of overhead and the cost of operations and make it fast and computationally light.
So in essence, you could be looking at, let's say, a front end of your IoT devices running on a back end of Geeq blockchains, and you could have your web page almost running and your API calls firing via JSON or AJAX or however it may well be that you guys are developing this. And I'll learn, of course, over the time. But multi-seconds or milliseconds, as it would be actually called. I'm trying to sound clever, and I wasn't there.
Yeah, that's the hope. We're writing this in Rust, which is of course sexy right now. But the reason it's sexy is that it's a very structured, very formal language that if you make a mistake, it doesn't tolerate it. It tells you that you've made a mistake. So it makes vulnerabilities much more difficult to create accidentally. It's also sort of natively designed to work with both RPC, and it works very easily with Captain Protobuf. So the whole stack is actually just sort of singing together and happily harmonizing, and it's also computationally very efficient in runtime. Another reason we chose it.
Oh, wow. So on that note, then, I mean, what's taken the most time, or has been the hardest object or objective or roadblock in the way to get to where we are now?
Yeah, it's sort of funny. I mean, the hardest thing is knowing where you're going. Getting there, it takes some time, but it's not as hard. It's work, but it's work that people understand how to do. Understanding what you're supposed to do, that takes time. So those tasks specifically are, and this is where I've spent most of my effort, years ago, developing the math of the protocol, improving its properties and so forth, its information properties, properties. That was a good year or two. That was a while ago. Now it turns out that that's nice for a theorist, but what you actually have to do is to say, fine, now what is the message that you're trying to convey, and what defines that it's a true message, and how does it relate to the chain, to the existing ledger state, to other transactions, and so on. And you gotta say it all. You leave anything out, and then that's a vulnerability. It's an exploit, right? So Captain Protobuf and Rust are intolerant. They don't let you screw around. So writing those, they're called templates. They're message templates that have the data, and it's what the data means, how it's used, how it's processed, and so forth. So that took quite a few months, and we're about 80% done with that part. We're done with the specification of that, and we're about 80% done with writing the protobufs themselves. The next part of the sort of foundation where you're going part is the transaction logic and the block writing logic and the message flow and the workflow and so forth. And these are things that you describe that would then be implemented in code, implemented in Rust. But first of all, I'm asking you to write a piece of code, Kieran, I got to say, by the way, the code here is trying to add 1 and 1. I say, I want some code that does a thing with numbers. It's not good enough, right? So you have to actually tell you what it's doing. And so that understanding that in a complicated structure of many types of messages and a large, that again, you can't mess with it. It's got to be exactly right. So Ian Smith, our chief developer, and I have been going back and forth with me sending him something and him saying that's incomplete, and me saying crap and sending him something else. So that's taken a while, and that's about 80%. So that part is, my part of it is probably, I'd say 60% done. His part is about 10% done because he started to write code on the basis of the parts that are the clearest.
Okay.
Yeah. So, and then the visible part of it is the last video we showed was this sort of elementary messaging network. So we implemented a basic messaging network that has a cut down client, cut down message space, and the protocols for communicating. It writes a type of ledger and so forth. So now we know that we've got this, protozoa that we hope will grow into an elephant, but we've got this basic life form that is eventually going to become what it is we need. So those are the things that are in the can. Right now, the major effort is writing up all of that code that goes into the Node client. So that's our current project, and our goal is to have a full testnet cloud implementation of a basic version of the chain. We hope by the end of January, beginning of February, and this will be something that, think of it as, if we had a protozoa before, this would be a kitten that can walk around on its own and support itself and act like a cat, but still needs some help.
You've still got to give it its good behavior and its rewards. I get you. I got you.
Exactly. And then eventually you'll build this into a tiger, but that'll take some time. Yeah.
I like that. That'd be bad joke time. That'll be rawsome.
Okay.
I've completely killed it. Sorry. So when you go down that, then with how you guys are building from the ground up, and as you said, you're literally writing as to what your needs are. Does this mean when you've looked at other chains and you've gone over like source code that is available, have you found that anybody has done something like this before, or are you literally creating a brand new wheel that is not spherical but a gazillion sides because it works more efficiently?
So there are similarities, of course. We haven't invented any cryptography, so we've taken cryptography off the shelf because we're not good at that. That's somebody else has to do that for us. We haven't written the transport layer. We're using RCP and maybe some TCP. Yeah. So of course we're not doing that network level. The Captain Protobuf is off the shelf. Rust is off the shelf. So we're taking all these tools. We're not inventing any of that stack. What we are doing, though, is from there on, our ledger structure is very different from existing ledger structures. It's actually a ledger. It's not like Bitcoin. So we have records of many types that are in the ledger that are updated to create new ledger states. Because we don't have proof of work and we don't have voting as our consensus mechanism or proof of stake, the structure of writing and then knowing whether or not you've achieved consensus is something that is unlike anything that exists. But the blocks themselves and the ledger itself, it's different, but it's not, it's the same species of things that are out there. But it's different enough that it's better just to write it ourselves in Captain Protobuf. So yeah, it's not the case that we can grab somebody's C implementation of Ethereum and tweak it and get something. We would have to tweak about 80% of the actual consensus and messaging code to do that.
Okay, wow. So in essence, it's more a case of taking almost like every major leap in technology that we've had, though, over the last few decades. It's taking something that works and just significantly improving it, but also not just improving it, is future-proofing it as well.
Yes, that's true. And but I guess the difference might be something like this. It might be the difference between, let's say, a Cadillac and a Tesla. So Cadillac's an awesome car,
Yeah.
but it runs on internal combustion. It has wheels similar to a Tesla in that, but you wouldn't want to take a Cadillac and then retrofit it to be a Tesla. Tesla is really a basically different technology.
Yeah.
Better in some ways, maybe worse in other ways, but it's a very different technology, even though it's still a car. And that's what we are. We're like that. We're like a Tesla. We're a blockchain that does the same kinds of things. Some ways are similar, but the guts are different enough that we have to start from zero.
Oh, I like the explanation. That's good. Using vehicles. Everyone likes cars. And then, I mean, I made a note beforehand when I'd watched over the first video, and the note I've left for myself, hopefully this makes more sense to you now because I haven't refreshed on the original video, but I've left a note saying that you've chosen to use a different transport protocol. Why was that? And why not TPPS or TLS or S, that sort of thing?
So mostly what you'll find is HTTP, and HTTP is ubiquitous, it's flexible, it's robust, it's awesome, I'm all for HTTP. But the cost of making anything that's general is that it's not really a sharp tool for whatever purpose that you're looking at. It's just a very good general tool. If you want to stream video on the one hand and deliver static web pages on the other, and encrypted packets, and on and on and on it goes, HTTP is your man. It's awesome. On the other hand, RPC, this remote, so this is really designed specifically with communication between devices in mind. So it's a query, it's a response. They're data minimal. They're designed to be very quick. They come in on a different port. But you wouldn't want to stream video on this. It would be terribly, terribly inefficient to do that.
Yeah.
But if all you're doing is having data packets that are static, like a transaction request or giving you a piece of static data like a block, this works terrifically well, and it's quick, efficient, and that's what we're after.
Do we find then that as the more that you're going along this route of creating things and building things, that you are keeping to a certain type of data structure, or are you thinking that although if we disregard music and video streaming, but if we look at you're looking at Word or you're looking at variable character messages, or is it going to be entirely almost timestamp and this item was removed at this time or this was done at this time? What sort of other the data levels, is there a limit on how much data you can project here if it's just text and variable characters?
Well, so the blockchain so I always say blockchain is really just a data service, and it's a version of a distributed spreadsheet or a version of a distributed database. And databases can have arbitrary size and arbitrary information, and database doesn't know that it's a movie. It's just a byte stream that it can deliver to you if you want to. So blockchain is the same way, except it's optimized for particular uses. So if you could put the Terminator into blockchain, but it'd be a really stupid waste of blockchain space, and it'd be very inefficient to pull it out of blockchain because it's just not designed to do that. It could do that, but it's just not the right use. So blockchain is really designed as a ledger, and that means it's designed to hold structured data that's indexed in certain ways, searchable in certain ways, and gives you certain utilities. Confirm, for example, that your bank account has a certain amount of money in it and that you have appropriate access to it. And it doesn't want at the same time to play you Taylor Swift.
Makes sense.
But it really is designed for those narrow uses, and it does those things in a way that's both secure and efficient.
That makes sense. Okay, yeah. So with brain went blank then for a second. What have I got? So on my next note, then let's have a look. You've completely blown my mind with a lot of intricacies. It's good. It's I'm never usually speechless. My wife would say the same if she was in the room. It's like, how's this happened? So with this, then of course we've got base layer protocol. We have then also having your chains built on top. Are you finding that you're going to attack base level protocol code first, or are you going to be looking at building everything as you go to make sure everything's working alongside each other, and you haven't written your base layer or your foundational code before realizing that something doesn't quite compute or work?
So yeah. So are you speaking of this sort of base layer that's sort of a source of consistency that's
Yes.
being discussed?
So will you be writing, like, is everything going to be written alongside each other? Will you work on a layer at a time almost? Yeah.
So that I think that idea of base layer protocol is a good one. I'm not so sure. So I guess I say that we are doing that too, but we're implementing it in a way that I think is a little bit better. Okay. As I've read, and my understanding is not complete, so I may be not describing what the other correctly. But the idea of a blockchain or any data source as a source of consistency, that we all can agree that whatever is in this record is the actual state of your bank account or contract or whatever it happens to be, and we can share that, and we can verify it, and we can prove it. All those things are part of base layer protocol, and that's awesome, and we're certainly gonna do that part of it. But added on to it, at least as I read it, there are certain types of smart contracting structures, certain sorts of transactions, certain kinds of governance and agreement. There are things that are layered on top of it that I think should not be part of the fundamental structure of the protocol. Because the needs change, they're very specific, and they also introduce attack vectors.
Yes.
And so I just don't like that approach. So our approach is this: we have this verification layer, and it stores transactions in Geeq, and we have within this, actually we do have a little bit of interesting things. We've implemented multi-sig. We've implemented multi-sig natively in the chain. We've also got something called a bearer token, which we'll talk about later, and some other things that are native to that. But everything else goes on an application layer. And the simplest application layer would be this idea that you would simply record hashes of events. So I know that your contract is signed in a certain day at a certain time and so forth, and the hash is recorded, not deniable, it's provable, and so on. And if you want to write something, I think, better off the chain as an application that does complicated processing of documents and distribution of documents and emails people and reminds people and all that stuff, that's great. It doesn't really, to me, belong on the chain. What the chain should be is to say, yeah, I did that. No, you didn't do that. Yeah, I did. And the chain should be the source of proof and honesty and proof and consistency. Not the thing that processes these things. This chain is expensive. If you're going to do something on Ethereum, it already cost me $4 to do a multi-sig on Ethereum. Are you really going to do every action within the office on Ethereum? And it's too expensive. So it's just not
the logical,
not the right use to me.
No, so, that makes sense. Wow. I mean, I guess then we should probably kind of talk a little bit about where we're up to on like the core development almost as now. I mean, is there anything you can maybe share that or update the people with at the end of the year and see what we can tell them? We have about top of the 80% and the 20%?
Yeah, well, that's pretty much the report. Just what I said there, that we've got the tadpole. We've got the basic communications network. By the end of January, early February, we're going to have the kitten. I should be careful. I don't want to name these things.
Geek kittens everywhere.
But what we're doing is we're writing the two major parts of it. Really, are two of the major parts of it are data structures and data logic. Yeah. And so the data structures are about 80% done. The data logic is about 20 or so % done, and we're hoping to bring the kitten level structures and logic to completion by the end of January, February.
Fantastic. Well, I guess that's pretty much covered, I think, as much as we'd both like to talk about there, I believe.
Okay. Well, good. Yeah. Well, actually, thanks for asking the questions. I see you've got Christmas in the background there.
Way too much of it. The joys of children. There's the snowman somewhere. There he is. Oh dear. Well, thanks ever so much for joining us, John. There's your Geeq update for the end of year 2020, of course. Merry Christmas and a Happy New Year, everybody. And see you in the new year from Geeq.
Bye-bye.
Bye.